After studying this module, you will be able to know more about reducible representation, their importance, why it is needed. And you will also learn about irreducible representation, their meaning, what we mean by the irreducible representation. You will be able to know also what is a relation between a reducible representation and irreducible representation, and what is the need for irreducible representation. In this module also you will learn about equivalent representation. That is, sometimes it is possible to generate representation using different bases, but later on we find that these are equivalent representation, only basis has been changed. In module 18 we have learned about reducible representation and what are various ways of getting these reducible representation. There are infinite number of ways of getting reducible representation. Now we will learn how to represent these reducible representation. Besides p orbital functions or d orbital function as the basis for representation, we can even have totally symmetrical s orbital function as the basis for representation. The general symbol for matrix representation is tau. This symbol does not represent only a single matrix, but a set of matrix using p orbital as the basis, d orbital as the basis, or 3n vectors as the basis, or using f orbital function as the basis or s orbital function as the basis, that is, which we can just put down as a subscript to the tau. Reducible and irreducible representation. If similarity transformation of a tau matrix can be factored into smaller dimension factor of m is to m matrix, where m is less than n, then tau n into n is called a reducible representation. And if tau n into n cannot be factored into smaller representation by similarity transformation, that it is called irreducible representation. Factoring of a larger matrix, say B matrix corresponding to R, of reducible representation tau reducible can be expressed as, that is, A inverse B than A inverse. That is, I am taking similarity transformation of the matrix BR by A, and by doing this I am able to factor the larger matrix BR into smaller matrices B1R, B2R, B3R. These can be done by just carrying out the similarity transformation. That is, I am able to get the block matrices which are related by similarity transformation. This similarity transformation just reduced the larger reducible representation to the smaller irreducible representation. The overall character of the matrix does not change due to similarity transformation. Diagonalization is shown in the diagram over here. B is diagonalized as B1, B2, B3, which are shown into the dotted lines. And matrix B is reducible representation and B1, B2, B are irreducible representation. Each of the lower dimension BR may be represented by tau1, tau2, tau3 representation of the point group. The whole transformation may be written as BR is equal to B1R direct product B2R direct product B3R, or tau reducible is tau1 direct product tau2 direct product tau3. Here the symbol which is written over here does not mean a plus sign or a multiplication sign. It is simply a direct product which has been taken. Meaning of the direct product has already been explained in earlier models. So tau reducible can be reduced to tau1, tau2, tau3 representation by making use of similarity transformations or taking different basis set. In general, we want to reduce tau reducible as far as possible so that it cannot be reduced further. We need to reduce the reducible representation into irreducible representation. During similarity transformation, a reducible representation may be reduced to equivalent irreducible representation. Let tau1 is repeated a1 times, tau2 is repeated a2 times, and tau3 is repeated a3 times. So tau reducible can be written as a1 tau1, then direct multiplication a2 into tau2, then a3 into tau3, or tau reducible is summation ai tau I, where ai is the number of times tau I or its equivalent repeats into tau reducible. Thus tau I is non-equivalent irreducible representation. Now to explain this, let me take the d orbitals as the basis. D orbital radial function in Cartesian coordinate systems, we can say that d1 I am just writing down dx square minus y square by 2, d2 is dxy, d3 is dxz, d4 is dyz, and d5 is dz square. Now, by making use of these d orbitals as the basis, we have generated 5:5 dimension matrices for C3V point groups by taking d orbitals as the basis. In earlier modules, we have gone for this, and we have got this representations for sigma V, C3, C32, and sigma V dash like this. We have developed all these matrices earlier. These are 5:5 dimension reducible representation, and 5 d orbitals have been used as basis. These higher dimensional reducible representation can be reduced to lower dimensional representation by taking different set of bases function, that is by making use of similarity transformation. If we take d1 and d2 as one set of bases, d3 and d4 as another set of bases, and d5 as another set of bases, then it is possible to factorize the larger reducible representation into smaller factors. This gives 2 is to 2 dimensional and 1 dimensional irreducible representation. That is, after factoring a 5:5 dimension matrix corresponding to any of the symmetry operation of C3V point group by taking d orbitals as the basis can be factored into 2:2 dimensional, then 2:2 dimensional, then 1 dimensional. That is, a 5:5 matrix representation can be factored into 2 dimensional plus 1 dimensional. That is, total I am having 3 factored irreducible representation. And dz axis, as you know, it can be factored separately. So by just taking out of the 5 d orbitals, d1 and d2 forms the one set, d3 and d4 forms the another set basis, and d5 forms another basis functions. Thus, we can factor a 5:5 d orbital matrices on C3V point group into 3 irreducible representations of dimension 2 and dimension 1. And these matrices which you have got, they have now the same, they are related by similarity transformation with each other. Similarly, we can take the example of C3b point group, and in C3b point group, again we are getting, by making use of this p orbitals as the functions or Cartesian coordinates as the basis function, we can factor a 3 to 3 dimensional matrix into C3b point group into 2. One is of 2 dimension and another is of 1 dimension. That is, 3 to 3 matrix can be decomposed by similarity transformation into 2 irreducible representation. One is that of dimension 1 and other is of dimension 2, and these are shown in the table. Thus total, and we also see that total character remain the same after performing similarity transformation. We can similarly you can go for other types of this reducible representation. If we have C2b point group, simple water molecules, in which we take x, y, z axis as the basis for representation. Here we can reduce into tau 1, tau 2 and tau 3. That is, each x, y, z axis can form basis separately for tau reducible, and then it can be reduced.
You already know about reducible representations and what are various ways of getting these reducible representation. There are infinite number of ways of getting reducible representations. Now you will learn about how to represent these reducible representations. If by similarity transformation, a tau n cross n matrix can be factored into smaller dimensional m cross m matrix, m less than n, then tau n cross n is called a reducible representation, and if tau n cross n cannot be factored into small representations by similarity transformations, then it is called irreducible representation. Factoring of larger matrix Br of reducible representation tau red can be expressed as given: B1R, B2R, B3R, etc. are block matrices and related to Br by similarity transformation, and zero matrix represents rectangular array of zeros. Similarity transformation produces the block diagonalized matrices, which are square arrays. The overall character of matrix does not change due to similarity transformations. Digitalization is as shown. Each of the lower dimensional BRs may be represented as tau 1, tau 2, tau 3 representations of point group. This whole transformation may be written as given. The symbol means a direct product has been taken. It is not the sign of addition or multiplication. This can be read as tau red representation and can be reduced to tau 1, tau 2, tau 3 representations by making use of similarity transformation or taking different basis set. In general, our aim is to reduce tau red as far as possible so that it cannot be reduced further. We need to reduce the reducible representation into irreducible representations. During similarity transformation, a reducible representation may be reduced to irreducible representations. Let tau 1 is repeated a1 times and tau 2 is repeated a2 times and tau 3 is repeated a3 times, then it is written as given, where ai is the number of times tau I or its equivalent repeats in tau red. The tau I is non-equivalent irreducible representation. Moving further, let us now examine the reducible representation generated by taking d orbitals as the basis. The d orbital radial functions in Cartesian coordinate system without common constraints are as written. Matrices for some of the symmetry operations of C3b point group are as shown. All these matrices are 5 by 5 dimensional reducible representation, and 5d orbitals have been used as bases. All these higher dimensional reducible representations can be reduced to lower dimensional representations by taking different set of basis functions, that is, by similarity transformations. If we take d1 and d2 as one set of bases, and d3 and d4 as another set of bases, and d5 as another set of bases, then it is possible to factorize the larger reducible representation into smaller factors. This gives two 2 by 2 dimensional and 1 dimensional reducible representations. Some of the factorized matrices can be written as given. Let us now take dz square on central atom and perform some symmetry operations of C3v point group. All these symmetry operations do not change or shift the dz square orbital. It means transformation matrix is 1. As we had a look that we obtain one-dimensional matrix, similarly if we take dxz, dyz orbitals as the base and perform sigma v dash symmetry operation of C3v point group, we will get a matrix of the type as given. Thus, dxz, dyz orbitals do not mix with other d orbitals and these transform among themselves. If we take d x2 y2 and dxy orbitals as the bases, these will transform under the effect of sigma dash y. According to matrix, thus it is clearly seen that d x2 y2 and d xy orbitals do not mix with other d orbitals. Using all 5 orbitals as bases and performing sigma v dash, we get the matrices as shown. We get 3 lower dimensional representations. One is of dimension 1 and the other two are of dimension 2. Our next step is to write matrices corresponding to symmetry operation of C3v point group using position vector method. These are as given in table. All these 3 by 3 matrices which are shown in the last slide can be decomposed by similarity transformation into two irreducible representations. One is that of dimension 1 and the other is of dimension 2. These are shown as in table. Thus, total characters remain same after performing similarity transformation. Now, if we take 3 unit vectors xyz along xyz axis, then z unit vector forms the basis for one-dimensional representation and x and y unit vectors form the basis for two-dimensional representation. And if we take C2v point group and the representations generated by taking 3 unit vectors xyz axis along xyz as shown below and decompose it into irreducible representations, you will get 3 irreducible representations of one dimensions only, for which xyz units are the bases respectively. Irreducible representations are the basic components from which all representations can constructed. Irreducible representations are of pivotal importance. With the proper choice of basis similarity transformation, one can reduce the reducible representations easily and properly. With proper first choice of basis function, reduction of reducible representation is not necessary.
Irreducible representation are the basis component from which all representation can be constructed. Irreducible representation are of vital importance. With the proper choice of basis function, basis similarity transformation can reduce the reducible representation easily and properly. With proper first choice of the basis function, reduction of irreducible representation is not necessary. Thus, in this module, we have seen what we mean by the reducible representation, what we mean by the irreducible representation, how reducible representation and irreducible representations are related with each other. I have taken the example of d orbitals as the basis for representation in C3v point group. Here we get 5:5 matrix representation, and these 5:5 matrix representation can be reduced into irreducible representations, 2 of 2 dimensions each and 1 of 1 dimension each. That is, taking d1 and d2 as the basis, we get one set, Taking D3 and D4 as the basis, we get another set, and taking D5 as the basis, we get another set of irreducible representation. Thus, larger reducible representation can be reduced to irreducible representation, or by performing similarity transformation on the larger reducible representation, it can be reduced to lower dimensional irreducible representation. And in the end, we can say that why these irreducibles are very important, that you will learn later in later modules on this subject.